So let's continue looking at linear transformations and how to represent linear transformations as a matrix. In this particular example, we're going to look at a linear transformation. That's what LT stands for. We're going to denote this linear transformation by T, and this linear transformation takes vectors in R3 and outputs a vector in R4. So the inputs to this linear transformation T are all of length 3, but the outputs are all of length 4. And we're told some interesting information about this linear transformation. We're told the following. We're told that the linear transformation of the vector E1 results in this 4-element vector, 3, 2, -1, and 0. When we use E1, that's actually a very special vector. E1 is always a vector whose first element, that's why it's subscript 1, E sub 1, whose first element is 1 and every other element of the vector is 0. Since this linear transformation takes elements in R3, then we know that E1 is going to be a vector of length 3. So up here we've written down E1, it's going to be of length 3, and its first element is going to be 1, and all other elements are going to be equal to 0. In addition to this, we're also told some other things about the transform involving E2 and E3, so let's go ahead and write those down. E2 is defined similarly. Since we're working in R3, it's going to be a length 3 vector whose second element is 1. And the same thing for E3, it's going to be a length 3 vector because we're working in R3, and its third element will be 1, and all other elements will be 0. That's the definition of E3. So we're also told that the transformation of E2 is equal to this vector, and the transformation of E3 is equal to this vector. So we know some information about this linear transformation. The first question we're asked is to find the standard matrix representation of this linear transformation. Anytime we're dealing with linear transformations, we can find a matrix representation of the linear transformation. By definition, the standard matrix representation is always equal to a matrix of the following form. The first column of the matrix representation is the linear transformation operating on E1. The second column is the linear transformation operating on E2. The third column is the linear transformation operating on E3. And we would keep going in general. The fourth column is the linear transformation operating on E4, fifth column on E5, etc. For this particular example, though, if we apply the definition of the standard matrix representation, we only have to do 3 columns because this is a linear transformation that takes things of length 3 and outputs things of length 4. So we're only going to have 3 columns here. So these individual linearly transformed vectors were actually provided in the problem statement. So constructing A is almost trivial. It's really just applying the definition of what we mean by the standard matrix representation. So I can just write down the first column is this vector right here, the second column is this vector right here, and the third column is this vector right here. So this is the the standard matrix representation of this linear transformation. We can check, just to make sure we did this right, it's almost trivial to check, but we can check what does it mean to take the linear transformation of E1. Well, in terms of the matrix formulation, it means take A times E1. If I take A times E1, I write down A, I multiply it by E1. E1 is 1, 0, 0. We know how to do this matrix multiplication. This says to take 1 times the first column, plus 0 times the second column, plus 0 times the third column. So essentially, this matrix vector product is going to return just the first column, which is exactly what we were told up here that the linear transformation of E1 was equal to. So this is almost trivial to check, but we checked it anyway just to make sure everything is self-consistent. So everything makes sense here. Let's do something a little bit more interesting. We know how to write our linear transformation in terms of a matrix representation. Let's deal with this vector now. Consider x equals 2, -1, 3. So here's a length 3 vector. We would like to compute the linear transformation of this vector. So how do we go about doing this? I could just plug in and compute ax. That would be one way to do it, and that would be perfectly fine. The way I'm going to go ahead and do it in this problem is to exploit the fact that we are dealing with a linear transformation. So to use that fact, first note that we can write we can write the vector x in this way. We can write it as 2 times E1 minus e2 plus 3 times e3. So we're just writing the vector x in terms of these kind of convenient bases that let us represent x in terms of these other vectors e1, e2, and e3. Because remember, e1 only has a 1 in the first element, so that's why we chose this 2 right here. e2 only has a 1 in the second element, so we can get the negative 1 here. And e3 has a 1 only in the third element, so 3 times that gives us that 3 right there. So let's go ahead and compute t of x. Well, to compute t of x, equivalently, I need to compute the linear transformation of this quantity, right? Because x is actually equal to that quantity right there. And now, here's what's interesting. This is equal to, because it's a linear transformation. You can't do this every time, but because t is a linear transformations have certain properties. They have a property that the transformation of a sum is equal to the sum of the transformations, and also any scale factors can be pulled outside the linear transformation. So this turns into a sum of 2 times the transform of e1 plus a negative 1 times the transform of e2 plus 3 times the transformation of e3, because I'm dealing with a linear transformation. This is really just the definition of what it means to be linear. This is something we know, this is something we know, and this is something we know. So we can go ahead and plug those in. 2 times the transformation of e1 is this, minus the transformation of e2, plus 3 times the transformation of e3. We know how to do scalar multiplication. I just multiply everything by 2, so I get a 6, 4, negative 2, 0. Minus this vector, plus 3 times this vector is 3, 0, 0, 6. Now if I add all these up, 6 minus 9 plus 3 gives me 0. 4 minus 4 gives me 0. And negative 2 minus 5 is a negative 7. And 0 plus a negative 6 is a negative 6. So here is the linear transformation of the vector x. I could have computed it just by computing a times x. That'd be one way to do it. But we went ahead and did it using the definition of what it means to be a linear transformation. This means that superposition and homogeneity hold, and we can write this equals this. The transformation of a sum is just a sum of transformations, and scale factors can be pulled outside of the linear transformation operation.